Hello, yes, it's Salah Nasri here, and yes, I have a special announcement. The game of chips has just hit 5,000 orders on Amazon. Thank you to everyone who placed the order. The book was just released in December, so I'm very, very grateful and surprised to date. If you are someone who is intrigued, curious about how the semiconductor ecosystem works from beginning to where we are right now, this book was written with you in mind. So order it, read it, and it is pretty much a handbook of the whole ecosystem. In the meantime, enjoy the next episode and don't forget to hit that subscribe button. But, one of the key topics is always going to be cost of ownership and throughput. Where do you suggest finding the best trade-offs between chemistry consumption, tool uptime, and defectivity, especially in wet processes and fine pitch assembly?
But first is that ask yourself why you select this packaging approach, and why do you really need this wet process? By the time you already invest in your infrastructure, you already had done all your manpower R&D that put into the process, it's too late. You can't really do a drastic change.
Our guest today is Dr. Tek Keng Lee, founder of LaunchTech.
This conversation explores leadership under manufacturing pressure, where AI ambition, capital allocation, and ecosystem constraints collide inside real production systems.
The human aspect is something that you cannot ignore, because there is always people that do not comply to the process procedure. Their process window is very small. When they start to run production, the yield is affected. The material property actually differ from the supplier data sheet. And once you are in that mode of production stop, and all eyes on you. As a leader, you have to clear the way, roadblocks, so that they can meet the milestone. You have to be just like octopus, trying to make sure that your team member is happy, the stakeholder is happy.
So what happens with the weak players in the team?
I think we have to give them a chance to move together. The standard always fall behind the technology. The difference supply chain is merging, and eventually I would think that everything will merge. The old concept of doing packaging is no more in packaging. You need to see packaging at the system level.
What would be interesting to know is actually which governance and IP practices keep research honest and commercialization fast. Hello, and welcome back to the Semiconductor Leadership Podcast. I'm your host, Salah Nasri, and whether you are a semiconductor industry veteran or someone who's just curious about semiconductor manufacturing, this is your podcast. So, before I start this wonderful discussion that is scheduled for you all, I have a very small favor to ask, as always. We've hit more than 200,000 views on the platform. Yet only 3% in the backend is subscribed. So do me that huge favor, hit that subscribe button. We are on YouTube, on Spotify, and Apple Podcasts. So, ladies and gentlemen, without further ado, it is with great pleasure today that I have the founder of LaunchTech and InnoCore Solutions, Dr. Lee. Dr. Lee, welcome to the show.
Welcome.
Excellent. Great to be here in Singapore. The weather is perfect, Dr. Lee.
Yeah, it's sunny and wet in Singapore.
Yeah, I like it. It's not like the dry desert of Dubai where I'm in at the moment. But yeah, no, Dr. Lee, I mean, the key thing I'd love to learn from you is look, your background goes from Texas Instruments to A-Star IME to Micron, and of course to launching the ITE and LaunchX Tech. I'd be intrigued to understand is what pivotal moments shaped your path in advanced packaging over the last 3 decades?
Yeah, I would think that the pivoting point actually came from A-Star as well as Micron. So I left Texas Instruments as an equipment and process engineer, going to explore R&D. And during my time in IME is actually the pioneer team, where we actually get a lot of scientists from overseas to come in to look into packaging. And in IME, I actually pioneered the men's packaging in Singapore. And that actually changed my perspective of looking at packaging. And that is where we spar with all those scientists, top scientists from all over the country, trying to understand the science of packaging. Because during then, I need to not have quite a bit of top-end equipment. So we had to really make use of the engineering concept, how to apply into that part of packaging. It's very different from today R&D, where you have all the top-end equipment, you get your data, you publish. But what we really do is really to understand the science. Take a very simplistic example that even for moisture, we came out to understand how material absorb moisture and how it actually expanded, resulting in hydrocelling, and how to put that model into a finite element model, just like any of the fatigue and stresses. So we actually make use of the engineering principle and to come up with new concept, new approach that packaging can actually be employed into this the sector. And Micron brought over Texas Instrument, and that was the seconded me back to start the FBGA, the substrate line in Micron, and that is where the evolution of substrate package during then that was about 20 years back. And I take care of the R&D as well as the global supply management for all the substrate, and because substrate was relatively new then, and this allowed me to innovate and really make use of all the concept that I learned in IME to really innovate and develop all the different package, inclusive of flat package, inclusive of thermal compression, the thermal compression bonding and so forth. And that actually changed my whole career, and I become very, very focused in semicon packaging, and that resulted in 140 US patent, as well as more than 50 journals and publications.
Wow.
Yeah.
Impressive.
So, yeah.
How does that make you feel now? I mean, you look at, I look back at our history in the industry, and we were pretty much the only semiconductor association, aside from IEEE ECTC, that were hosting semiconductor packaging senior executives globally since 2013 to date. And when we were doing this in 2013 until maybe a couple of years after the pandemic, people, especially the design houses, they used to say to us, Salah, you're too focused on advanced packaging or packaging. And since about 3-4 years ago, they're all joining us now. So they all want to get into advanced packaging. They all want to understand it. And now they're all, building departments dedicated to advanced packaging. Is this something that you've witnessed as well in your career as well?
I think there are two inflection points in packaging. One was the introduction of wafer-level CSP, which actually introduced the front-end RDL process into packaging. And that was way back in 2005 to 2007, where Infineon introduced the EWLP. And a lot of the old packaging guys don't know about RDL, because RDL is making use of some of the front-end equipment to do the lithography and so forth. So that actually changed a lot of perspective of how packaging is done until today. Another key inflection point came from the EUV, where EUV are not able to scale down in terms of the transistor size because the cost is getting a lot much more. You cannot shrink the die further, and that make packaging a good alternative to really assemble the different chip together. And typically we call this a heterogeneous integration that make it a more productive, more efficient, and more cheap to meet the size, cost, and performance of packaging. And that was the reason why today the hybrid bonding become very interesting, because it actually merged the front end and the back end together into one.
Yeah.
And I see that this is going to evolve further with the substrate, the fab, as well as the assembly all merging into one.
Yes, yeah. And what's your perspective on co-package optics, especially with the huge focus on it this year in specific?
Yeah, so although this is not key in Singapore because co-package is typically deal with server market and so forth, and you look at it is that this is actually driven by the AI.
Sure.
So because you need that part to do that processing, that part to translate the information to do that. And definitely co-packaging is one key part of packaging. Why? Because this package require the electrical performance, the thermal performance, as well as the pad pitch, because the I/O is relatively high, and you will require the different die to be integrated together into a package to do that. And that is a very challenging job to do it. And packagings will have to be the enabler to make sure that works.
No, that's fair point. Fair. Looking at your academic foundations, how did you've got the Bachelor's of Engineering at NUS, Master's Science at NUS, and a PhD at NTU. How did all of these influence your approach to solving hard problems in materials, interconnects, and reliability?
Okay, I think first is that we need to first understand that packaging is actually a multidiscipline concept. It don't really belong to electrical engineering, mechanical engineering, or material engineering. It actually integrate all the different engineering together. I take example. Corrosion is actually a very classic example of chemical engineering, where the electropotential difference of the materials, the electrolyte that result because of the moisture actually had to come in together. So, and that is where I would think that a lot of the university have difficulty actually putting packaging into a specific segment. Even today, whether it's Singapore University, Malaysia University, or even other university, is that it's always classified into one domain. But if you look at the semiconductor sector, in actual fact, it cut across. You need to know the electronic performance, you need to know the mechanical, the thermal issue, the mechanical issue, the material issue. So it's actually all integrated. And you need to be all-rounder to really and understand that broad-wide engineering discipline in order to really solve your problem, in order to pass the knowledge through. And that is where I think I'm trying to do my little fair part to contribute back to the semiconductor industry.
Marvelous. I mean, you've seen the industry move from DIP to QFP to FOWLP, final wafer level packaging, panel level packaging, hybrid bonding, and heterogeneous integration. I mean, which transitions were most disruptive from your perspective, and why?
Yeah. I would think that 20 years ago is really the RDL, and we are seeing the fruits of the RDL today. But what is exploding today is really the hybrid bonding. And this hybrid bonding really will change quite a bit of landscape in the sense that you can make use of the technology to heterogeneous integrate the different devices together by stacking them through that part of the hybrid bonding. And that make a lot of things to be very, very different from the old way of doing packaging. And that will mean that packaging is no more just packaging, but it really actually move this into a device aspect. And I think today a lot of company is exploring how hybrid bonding can be used to do that part of the heterogeneous integration. So that I would think is a pivoting point, and that will actually change in 10, 20 years time when this technology mature. the whole landscape will start to change again.
Yeah. That's the only constant.
Yep.
Change
is constant in semicon.
always.
And those who are slow will actually be left out, and that will mean MMA will take place and so forth.
True. You've driven innovations in fluxless flip chip and thermocompression bonding. What technical barriers, be it, the voids, oxidation, IMC control, did you have to overcome to make these processes production worthy?
Okay, this thermocompression bonding, which I developed, was quite different from a typical thermocompression bonding. This thermocompression bonding is actually a solid-liquid interdiffusion bonding, and that means that when a solid actually dissolute into a molten metal, there will be a lot of IMC formation. But this technology able to solve certain pet pitch issue, certain instantaneous bonding. So what I try to overcome the IMC is to do this interconnect in less than a second, so that the metal will not dissolute into a molten, and that will actually reduce the IMC. And from there, your joint improvement will actually improve. Or in that aspect, and you have the underfill or the NCP to redistribute the stress, and that will actually enhance your joint performance.
Indeed. And what's so interesting to connect this all together is that your track record of the patents, so 140 or 50 plus US patents, and of course the publications that you've done. What would you say, or which inventions best capture your philosophy, which I've been informed through the research my team has done, which is manufacturable innovation, and what business problems did they solve?
I would say that is the thermocompression bonding, because the thermocompression bonding that was developed was way back 20 years ago was quite unique in the sense that it solved the pet pitch issue. And other than solving the pet pitch issue, it also actually make use of a legacy machine of a plus minus 25 micron to do a 70 micron pitch, and that is 20 years ago.
Wow.
To do that. And that research actually is really a multidiscipline, because you are not only talking about the metallurgy joint, you also have to look into all the packaging materials that is suitable. And this whole innovation, when we started off, was actually on a flex tape. And that actually was sort of where Tessera in the old days was actually popular and was going round to protect the IP on the flexible tape. And in actual fact, that innovations was quite amazing. Because it's not only solved the pet pitch issue, it also solved a productivity issue in a flip chip, and as well as all the performance.
So what would you say, if we look at from paper to process, what's your playbook for turning a promising paper result into a repeatable SPC stable production process at 200 or 300 millimeter?
I would say paper is a lot typically very academic. Okay, but really, if you are looking at productivity yield, I would think that other than the selection of the technology, you will need to do a lot of process optimization to really looking at how to stabilize your process. But other than all the technical concern that you have, the human aspect is something that you cannot ignore, because there is always people that do not comply to the process procedure or what you have in place into it. But I would like to just emphasize that to look at it, you need to first make sure that this is the right technology and you have the right infrastructure and the process are stable. And the process window have to be wide enough. And I've seen a lot of innovations, especially in the panel level, in the wafer level, their process window is very small. And when they start to run production, okay, there is the yield is affected, because when they do the qualification, the window is not well defined in that aspect. So, and that is why I would think that if you understand the whole packaging flow, you need to ensure that you have wide enough process window to ensure that part of the process stability.
Now, what would be intriguing to understand is if we break it down into three areas. The first area that I'd like to discuss is, of course, the substrates, the second materials, and the third would be fine pitch challenges. So if we talk about advanced substrates, from your perspective, what are the critical levers in substrate design if you're looking at stack up, CTE control, surface finishes, for high density memory or logic and chiplet routing at fine LS perspective?
I would first see things quite differently because from packaging angle is that each application are quite different. I take memory for example. Memory is a low cost, is a commodity product. So the cost aspect will actually be the key as long as you meet that part of the performance. But if you are talking about HPC, high performance computing, the whole angle will be shifted. And that really means that the thermal electrical performance will be the first concern to look at from a substrate angle. And that will also means that the substrate, you will have to decide which substrate will be suitable for what application or for your needs. And definitely is that the cost of the different substrate today contributed a significant part of that whole packaging. And that will means that from a package design angle, you really have to see it from a totality perspective before deciding what would be the substrate. And the substrate, definitely, like what you mentioned, is that other than the substrate, your material, your CTE, everything come in because certain of that interconnect technology itself may not be able, the substrate may not be able to withstand the processing. And that will mean that there is a lot of such consideration or before you can decide which would be the right substrate, which would be the right interconnect technology for what application.
Yeah. And if you look at RDO and fan-out productivity, you've led productivity breakthroughs in RDO and fan-out flows. Which steps would you say, and I'm referring to like masking, plating, debond, rebond, offer the biggest cycle time and yield wins today?
I would think, seriously, if you look at panel level, warpage is the key concern because if you warp, you can't actually index down the whole production floor. And when we talk about panel, mainly is that we're trying to gain productivity through the increase of the number of chip per panel. And once you have that in that panel form, the size is huge. Yeah. And that will means that how to actually resolve the warpage so that you can actually process down the line, whether to use a carrier or to use materials or to use whatever process to do it. And being a panel is a lot of time you may not be able to do this manually because it's very heavy. And that will mean that the automation will have to come in to make sure that you can actually process that whole panel down the line. So in order for that to work, I think there is a lot of consideration other than the warpage. You also have to start to look into that design aspect because as such a panel, the tolerance is on the lithography and so forth will start to, because there's going to be a die shift and so forth. So you need to do that compensation to ensure that you can actually process that. And warpage is one of the main culprit as well. So that make wafer level, panel level a lot much more complicated than the old days of doing packaging where you only do it one on the strict form and so forth.
Yeah. And if you look at material characterization, I mean, which metrology characterization techniques are must-haves for correlating defects? So, for example, let's say interfacial IMCs or pad cratering with real-world reliability.
Okay, I would say first you have to classify this into metal as well as polymer. In metal, definitely is IMC. And in polymer, it's definitely the TG and the CTE 1 and 2, which is coefficient of thermal expansion. But to make things a lot more complicated is that a lot of such information are eventually fit into a finite element software, whether it's NCs or so forth, to do that part of the simulation. But a lot of time is that the person that is performing the simulations are not material science. They don't have material background, and they just take all the materials data that is from the supplier data sheet and then plug in, and you get what is out there.
Yeah.
But if you have been a material science and to do all the calculation, you will note that a lot of the time, the material property actually differ from the supplier data sheet. I take a very quick example in the sense that MGC substrate on the BT substrate is actually characterized at the core material of 0.8. But a lot of time when you do a package, it's actually using a core of 0.15 or 0.1. And when we all know that at the 0.1 mm core, the number of glass fiber and density is very different. And that will means that your TG and your CTE 1 and 2 is very different from a 0.8 and a 0.1 mm core. But all the simulations that is out there doing a BT substrate based on NGC simulation, NGC data characterization, and that make things a lot, there's a lot of error into this aspect. And if you're talking about material characterizations, one aspect that falls short is the interfacial adhesion. So the interfacial adhesion, a lot of time, is not easy to classify, to do that characterization. And a lot of time, finite element is only looking at material property, and interfacial characterization cannot be really put into that simulation model to do a better correlation. And that is where I think interfacial adhesion is very key, especially in the mode 1 fracture mechanics, which is a tensile mode. And if we can actually do a proper material characterization, that would be actually wonderful, so that you can actually characterize where the material interface will give way and under whichever relative condition.
I mean, Dr. Lee, I mean, if we're looking at designing for reliability, for advanced packages, which stress modes would you say that are most likely to surprise teams? I mean, would it be the HAST, HAST, would it be TC drop, or is it electromigration? And how would you de-risk them early?
I would say that first is that from a reliability angle, the different application actually differ quite a different focus on reliability. I would take, for example, if you are talking about portable electronics, your job tests become very critical. And that will mean that your interconnects and so forth will have to come in. But if you are talking about consumer, basically you just need to pass the basic reliability test. And you are talking about automotive, that actually have a very wide aspect, whether your device are in the engine, whether your device is entertainment or dashboard, and all these will have a different reliability condition. So you can't really say that which reliability test condition is important, but really you have to see is what application, and there is a series, and different application will actually have a different series of reliability tests or to be done to meet that part. And reliability test is really a accelerated test that trying to link your manufacturing's package reliability to the field application condition.
So if one of the key topics is always going to be cost of ownership and throughput, where do you suggest finding the best trade-offs between chemistry consumption, tool uptime, and defectivity, especially in wet processes and fine pitch assembly?
I would think that I think maybe just to do that illustration of electrolytic plating or pumping that you call it. So if you look at electrolytic plating, this itself will depend first is on whether you're doing it at the wafer or whether you're doing it at the panel. And what would be your spec in terms of the bump size and so forth. So, and first, when you start to do all these aspect, I think you have to go back even before looking at the process. But first is that ask yourself why you select this packaging approach, and why do you really need this wet process? Because everything must start from that technology that you select before your wet process actually come in. And if you have actually have a very wide base and understand your technology, if you can actually compare what would be the best approach. And each technology do come with their pros and cons, and that will also means that you really need to do the assessment before deciding, and not to wait until that you hit electrolytic plating and say, hey, this is not the right approach. And by the time you already invest in your infrastructure, you already had done all your manpower, R&D that put into the process, it's too late.
Yeah.
And that is a lot of time, that is what NNC actually face. And they may have to abandon, or they may have to revisit, is this the right direction? And that will also means that when you look into any packaging, it'd be good if someone is able to have that broad base to really assess the different technology before you really start into looking at the production level. Because at the production, you only can do more as an increment enhancement. That's it. You can't really do a drastic change. And in order to really save costs and so forth, that is where a new packaging technology come in, and that will actually revolutionize the whole solution.
I mean, what's interesting is that applying the academia to the real world, as one would say, you've managed global substrate suppliers and set up incoming quality systems. What would you say makes a world-class supplier qualification program? And what would be most interesting is what are the red flags?
So first, I would take substrate example. A lot of time, substrate is the end product. And when we started this way back in Micron, people don't really know how substrate is done. And you really can't control your end supplier, what they are doing. And you cannot be more familiar with them on the process as well. So the only way is that you have to put in gates at the different critical lock point at the end supplier, so that they can actually consolidate their data. But what's more important is really to make a physical audit to ensure that that they actually follow the process that they actually put in place. And a lot of time, whether you're talking about Japanese, Taiwanese supplier, Korea supplier, when you do the line audit, you tend to find a lot of things that different from what they have stated. And that is a very interesting aspect.
Yeah. That's red flags.
Yeah. And that is why I say is that audit is necessary, but you need a very experienced people that know the process
And understand.
in order to look at it, where is that red flag and what is the key things to look into. Because otherwise they will give you tons of data and you don't know where to look for in the production floor.
I'm intrigued to learn from you, like the lessons from, standing up labs at IME and the transition to Micron and now to ITE. How do you structure teams, or let's say equipment sets as well? And and also what would be interesting to include in this is milestones to accelerate tech transfer to production lines.
Okay, first I think when you talk about tech transfer and so forth, really you need to understand people. And from a management angle, you need to understand your team member, where is their strength. And that will mean that you will have to leverage on individual strength, put them in the right area so that they can actually grow from there. And definitely as a project lead and so forth, you have to set milestone, and you have to really do a proper project management, guiding the teams. And as a leader, you have to sort of clear the way, help them to clear the way, help them to clear the management anger, the management's roadblocks, the procurement issue, so that they can meet the milestone, and from there to keep the team morale high. And definitely is that your collaborator is very important, and the collaborator must trust that you are able to bring the whole team to meet what they want. Also, in a way, you have to be just like octopus, trying to make sure that your team member is happy, the organization is happy, the stakeholder is happy, and so forth, in order to do that technology transfer. And definitely, you also must also understand there is a lot of competition out there, and you need to really keep your eye open and see, is this still valid from time to time?
So what happens with the weak players in the team?
I think we have to give them a chance to move together. So, and as I mentioned, is that everyone do have their strength, and so you have to really understand where they can contribute or in that aspect, so that they can move along with the team, or so that they can actually progress with it.
Could you share like a non-confidential example where tight customer collaboration changed your process or architecture and led to measurable cost quality breakthrough?
I will see, maybe I will take substrate, okay? Because when the substrate have quality issue, what happen is that the line has stopped. And we always would think that the suppliers should know their process well.
Yep.
In actual fact, a lot of time, they just do it day in, day out, collect the data and so forth. And once you are in that mode of production stop, and all eyes on you. And that would really means is that you have to lead how to solve the problem.
Yeah.
And being a technical guy, you need to know, look at the failure observation, where would be the key process that cause this failure. And that already means is that you have to work together with your substrate supplier, which is your collaborator, to see, to tell them technically where it come from and what data to capture, and requesting them to collect the data and to do some of the failure analysis, as well as on the line, you have to collect the information, put it together, and you have to run some evaluation to reconfirm the problems before you can actually solve your issue. Because the main key thing is to make sure that you get the substrate back online, so that everything can flow.
And I think one of the common challenges that keeps popping up is this term of standardization.
Yep.
And I'm intrigued to hear what's your perspective on standards leadership. Where do standards most urgently need to catch up? Okay. And this could be, of course, as you mentioned previously, it could be like in the hybrid bonding, chiplet assembly, or even substrate test models.
Yeah, okay. So I'm actually currently the co-conveyor for Singapore Semiconductor Standard, and under IEC. And IEC is really a standard that the different country to accept for the different semiconductor industry. And in semicon, we have quite a bit of standard, whether it's SEMI, JEDEC, EIAJ, IPC, and so forth. And a lot of time is that regardless of all the standards are always fall behind, okay, the technology. And worse is that this at the country level, the standard is even further behind, because a lot of time at the national level, the IC standard actually take reference from all these industry standard to call for. And you like it or not, all these standards are actually talking about package that are maybe 5-10 years that already matured. And that will mean that today, only the industry standard trying to catch the hybrid bonding, the glass substrate, the panel size, the necessary of PLP, and so forth. So the standard is actually falling behind. And that is where I believe that there's a lot of semicon expert, whether under JDEC, under SEMI, trying to work out the different standard to be adopted. But that also means that at the country level, we need to really catch up, doing a catch-up game to really adopt some of this industry standard to be aligned.
But why are they not working in the packaging world in specific?
They are working, but a lot of time is that
They exist, but they're not
they
being
exist, but
adopted.
you see, at the country level, each country have their own perspective. I would take example, different countries, some may be very focused on automotive, so they are driving from their nation perspective. Some very focused on heterogeneous, but at the country level, if you don't have sufficient participate country in supporting the standard, it will not be adopted.
So, look, I mean, Dr. Lee, you've delivered more than 100 workshops across Asia and Europe. What core skills do you feel that packaging engineers still lack today?
I would think really is that these semiconductor packaging are always taught in one engineering discipline. But if you look at from an industry angle, semiconductor packaging is actually cut across the different engineering discipline, and it really tough for any lecturer to cover all the different angle. And that is where a lot of times what I'm trying to do here is to come in from a multi-discipline engineering angle to put the science behind semiconductor packaging, or rather than just going through how the panel or how the wafer level package is done. But what is the science behind all this? What is the challenges space? If you can understand the fundamental, then you can actually innovate to come up with new packaging solution, and you can understand how the technology actually evolve with time.
So how, I mean, Dr. Lee, from your perspective, how should curricula evolve to fill those gaps?
If we are given a free choice, I would say that the different subject expertise should really come in to link whether corrosion to chemical engineering, whether the polymer matter to material engineering, the thermal to mechanical engineering, and so forth, and the electrical performance to the electronics, so that all the different expertise can come together, so that they have a proper understanding why packaging is done this way. And a lot of time is that the manufacturing aspect of the different material supplier are done. And to make things a lot more complicated is that the semiconductor ecosystem is very wide and it's very complex. Not a single country own everything. You look at it, Japan actually own the material, right? The substrate are done in China, Korea, Taiwan, and so forth. So the OSAC is actually in the Southeast Asia region and so forth. So the equipment is in Singapore, context as a corporate, and the fab is in the Europe, US, and Singapore. So none, and that will really means that no one actually own the whole part of the semiconductor ecosystem.
So if we talk about building that talent pipeline, what do you feel is the most effective way to prepare upcoming technicians and engineers for heterogeneous integration and panel level production?
Okay. I would think that first is that the university can do what can actually upgrade their curriculum if there is if they are able to do so, and to offer this as part of that curriculum. And definitely being universities and so forth is very academic, and that will means that even you have the curriculums, a lot of times when the student go for interview and so forth, they haven't seen what is a package, how the package are being done, and how the sector is really done. The industry will have to engage with the university. And what I'm trying to do here is to set up this InnoCore solution. The InnoCore solution, the main thing is as a bridge to link the university as well as the industry together, so that we can provide more formal educations, trying to link the engineering discipline, which is today lacking, to that part of the packaging, and so that we can actually do a proper certification, so they can understand the industry, understand the terminology, so that they can actually easily to be merged into the semiconductor industry. And once they join industry, they can actually contribute back to the industry. How to do that?
Mate, I mean, it's a good thing to do. What's holding it back from making it happen?
Based in the core solution, just started only 2 weeks ago, and we are talking to respective authority to get that part of the funding. And we have been also sharing this under the IEEE chapter in Malaysia and so forth. So I think it will take some time to sort it out, but the setup is already done, and we are also talking to some of the university to do that.
Fantastic.
And hopefully that this program will work.
Fantastic. So you helped transform a flex PCB maker into a substrate supplier. This is what my team has sent me as the research. So what were the critical technical and organizational moves other CEOs should note from that?
Okay, for this specific company is that first, he actually acquired a technology, from an organization and he's not a technical guy. And when I was engaged as consultant, I was looking at this technology, and this technology itself was not very mature. And when they was adopt these technologies, when you go into production mode, it's a MIS, molded interposer substrate. These actually result in a lot of assembly yield issue. That means that in term on the per strip, the X out is not able to meet certain requirement and so forth. And because the technology itself is was not properly done from packaging angle, if you compare this with conventional substrate, it's much more complex. And what is the benefit other than that thermal condition and so forth? And looking at it is that but this, the owner is trying to using this to move from a flexible FPC perspective into the substrate business. And looking at this is that acquiring this technology is also a revolutionary, because it actually moved from PCB to substrate. But with that understanding of this technology, what I do is to leverage on what they have, the infrastructure, and making use of the ABF material and turn it into a collar substrate. And that actually gains certain advantage. And that actually helped them to leverage and move into the substrate business. But other than the technical issue, the other part of the challenge is really the culture. And this company, being a family business, will have to do quite a bit of repositioning, to as well as training to the engineers and so forth before you can actually take on this new technology.
Dr. Lee, your commercialization playbook seems to be a trait that really works well. I mean, evidently, you've also raised multi-million grants and licensed multiple solutions. What would be interesting to know is actually which governance and IP practices keep research honest and commercialization fast.
Yeah, so IP is a very important aspect. But a lot of the time is that you need to know what to file and how to file. It's not just talking about IP. Because a lot of the time is that the attorney will just do that crafting for you, but that doesn't help. So if you are really trying to protect your IP, you need to understand the landscape. Who is your competitor? Whether you're filing more from an innovation angle, or you're filing to prevent competitor to come in. And that would mean that what would be the angle to file to stop competitor to come in, so that they cannot get around your IP. And that would means that that is not what attorney do. And that would means that as a researcher or as a project lead, you have to really know how to craft it, give it to the attorney so that they will know how to position it together with, because they are not the subject expert. You are the subject expert. And that would really means is that you have to provide the scope, the area of how to craft it so that the attorney can actually put in writing or to help you to protect your IP in that aspect. Yeah.
So looking ahead next 3 to 5 years in packaging, Dr. Lee, from your side, what's the biggest inflections you see coming? Would it be hybrid bonding at scale, glass core substrates, chip blast fan out, or something else?
I would say that all this technology eventually will merge into it.
All of them, or merge into one, like a chiplet.
Yeah, I would say you look at it is that if you think very logically, today we have a package or a substrate or interposer to do a package. And why do we need a substrate or interposer? Is really trying to match the die pack pitch of the device. But if I have a glass substrate, I can do a 2x2 micron line space, and I can hybrid bonding. I can actually stack the die and put the different heterogeneous device together. And that would mean that my glass substrate can be a high density PCB. I can put my die without the substrate interposer directly on glass substrate. The glass become a PCB, and that whole thing may change the whole packaging solution. And you look at it, your substrate is merging, your OZ is merging, your front end wafer is merging. So I see that may be one of the direction that packaging will go in the long run, but that was actually depends on your cost and performance. But definitely some conventional packaging will still stay, or depending on the application and the cost in that aspect. But you are talking about eventually, I would think that the three technologies of front end, assembly, as well as PCB substrate work eventually merge together into one.
That'd be remarkable.
Yep. And we have been seeing this, that the different supply chain is merging.
Yeah.
From a different supplier become a substrate, from a PCB become a substrate, and eventually they move into embedded package and so forth. So, and we can also see that the foundry fab is moving into advanced packaging. And eventually, I would think that everything will merge.
So with AI driving power density and thermal stress, how should packaging teams globally rethink interconnect architectures and reliability screens?
I would say that first is that for AI or HPC, it will always be electrical and thermal performance. And that would really means is that to do this part of the packaging, you really need to be very different from old days. You need to really know at the system level what is how the electrical is done, how the thermal is done. It's really done. The old concept of doing packaging is no more in packaging. You need to see packaging at the system level. And that means that is not only interconnect materials, you need to understand how this whole system is functioning. Just like a MEMS device. If you do a MEMS packaging without understanding the MEMS, you cannot do a MEMS packaging. So eventually packaging will be done at the system level, and that will mean packaging will have to see things at the system level, and you cannot be saying that you just look at memory, you just look at microprocessor. You have to see this integrating together at the system level, and that would really means is that you need to really understand the electrical function, understand the thermal function, understand the interconnect materials all come together in order to make this part of the heterogeneous integration, this part of the chiplet design work.
Dr. Lee, it's really been a very, I feel like I'm back at university again. It's been a wonderful discussion. My last question for you is what's your single best piece of advice for engineers and entrepreneurs tackling advanced packaging today?
I would say that innovation, is the key. to survive. We all know that semiconductor packaging, okay, or semicon industry is a throat cutting business. And that will mean that you have to innovate to stay ahead of the curve, especially against all your competitor out there. And that will mean that you really have to continue to innovate to stay ahead. That is my advice to everyone. And that will also means that you cannot stop learning.
Yeah, definitely. Do you have any last comments you would like to share to the world out there?
I would say that let's see what will happen next in the semiconductor packaging world.
Sure. It's the like I said, it's the only constant in the world is change.
Yes.
So expect change. Dr. Lee, thank you for joining us on the Semiconductor Leadership Podcast. It's been absolutely a pleasure to speak with you.
Yeah, most welcome. Thank you very much.
To the audience, to everyone watching, thank you for tuning in. If you want to get in contact with Dr. Lee, his LinkedIn profile is just below. You can click here and connect with him. As I always say, it takes a village to raise a chip. So please, if you found this of interest, share, like, and comment. Other than that, thank you for joining us. Take care and see you at the next episode. Bye for now.